Let's apply what we've learned about powers in AC circuits using the two circuits that we've used before, the series circuit and the parallel RLC circuit. Let's begin with the series RLC circuit. If you recall, we have this solution for the series RLC circuit where we were able to solve for the impedance, the voltages across each circuit element, and the current, and also the phase angle. We were also able to determine the function for the current, the resistor voltage, the inductor voltage, capacitor voltage, and the source voltage, from which now we can determine the power across the resistor, or the power dissipated by the resistor, the power across the inductor, the power across the capacitor, and the power in the source, power provided by the source, and also the power factor. So those parameters are easily solved by simply using the following equations. For the source, we know that we can use I, the current I, times V sub S. For the power across the resistor, the power dissipated by the resistor, it's I times V sub R. For the power across the inductor, it's I times V sub L. The power in the capacitor, it's I times V times C. And of course, for the power factor, that's easily solved to be the real power divided by the apparent power. Okay, so if we use again, it's easier to use tools that are already available, such as MATLAB. And by using MATLAB, I was able to draw this power triangle where you should see the real component of the power shown as the blue phasor, the reactive power shown as the magenta phasor in magenta, and the apparent power shown as the green phasor. Okay, and from there we were able to compute for the power factor to be equal to 0.76. Okay, in the upper right figure, you'll see the curve for the current, the waveform for the current, the voltage, and the power. The power curve was obtained by simply multiplying the sinusoidal waveform between the current and the voltage. The y-axis is in watts, so it displays only the units of the power, but the scale is the same for the voltage. You just use units of volts. And for the current, the scale is multiplied by 10 because the current is actually 10 times smaller than this. The x-axis is, of course, theta. And you see in this curve that the waveform for the power is purely dissipative. It's only along the positive y-axis. If we compute for the magnitude based on the values that we've used before, so for the power across the resistor, we have 5.1 amperes. That's the current that we computed before. And the voltage across the resistor is 61.2 volts. This is the actual amplitude. Okay, and since if we do the mathematics, this is 312 watts. But if you look at the figure, the power is actually approximately 317 watts, which is about the same, probably just due to some rounding off error. In the upper right figure, you see the power in the inductor. You see that the current again is scaled by 10 and the voltage is scaled by 1. And the power you obtain by multiplying the current and the voltage waveforms. The current is out of phase with the voltage by 90 degrees, with the voltage across the inductor leading the current. And you can see these alternating power from the positive to the negative to the positive to the negative, meaning that it's consuming power, and then it's returning power, and then it's consuming it again, and it's returning power. And that's for an ideal inductor. If we do the mathematics, if you recall, the values that we obtained for the current is 5.1 amperes, and for the inductor, it's 240 volts. Okay, this will give us around 1224 volts ampere, but in the figure, okay, you can clearly see that it's not 1000 to 1.2 kilovolt amperes, but it's about 312 watts. And the reason for this again is because there's a shift. So the amplitude of the maxima of both the current and the voltage are not in phase, and therefore the maximum amplitude occurs only at these angles where the current and the voltage where the current and the voltages do not have their maximum values. Okay, what about the lower left figure? The lower left figure shows the capacitor. So again, we can obtain the power in the capacitor based on the values we've computed before. This is equal to 826 volt amperes. But again, in the figure, if you look at the figure, then this is about 421 watts. Again, the reason for this is that the voltage and the current are out of phase by 90 degrees. So the maximum of these values occur when the current and the voltage, well, they're not at their maximum. Okay. And finally, for the source, or for the apparent power, we have 5.1 amperes times 100 volts, which is the given quantity. This is about 510 watts. But in the figure, we have about 416 watts. Okay. Now, in this figure, the current and the voltage are out of phase by 51.9 or 52 degrees. Okay, and since they are out of phase, the power that is dissipated, or power that is provided by the source also has a dissipative component and a return component. The return component is actually the difference between the reactive power in the inductor and in the capacitor, and that's a result of the of taking the difference between the inductor and the capacitor reactive reactances. Okay, and you notice also that there's more dissipative power compared to the return power. The return power is naturally coming from the interaction between the inductor and the capacitor, and the dissipative power mostly comes from the resistor, but because the inductor and the capacitor are also trying to get as much power as they want, okay, so there's some sort of there's some balance that they have to achieve. So there's also some dissipation that is occurring between the exchange. Okay, now let's take a look at the parallel series circuit example. If you recall that in this example, we have a voltage source of 5 volts and a frequency of 12 kilohertz, and a resistance of 100 ohms, an inductance of 15 millihenry, and a capacitance of 0.022 microfarad. We've already solved these quantities before. The conductance, the susceptances, and the admittance, and also got the currents, and also finally got the impedances. Okay, and from there we were able to graph the phasor diagram and the sinusoidal waveform. Okay. Okay, now again using MATLAB we can solve for the power across each of the circuit elements, and the power across the resistor, or the real power across the resistor, is shown in the in the lower right box. If we try to solve for the power across the resistor, then we have 5 volts times the current, which we already solved before, to be 0.0500 amperes, and that is equals to 0.2500 watts. And in the figure we have the power to be equal to 0.2500 watts. Okay, and for the inductor, the power is obtained by multiplying 5 volts by 0.044 amperes. Okay, this gives us 0.0221 watts, but in the figure this power is seen to be 0.0111 volt amperes. Okay, and for the capacitor we have 5 volts times 0.0083 amperes, which gives us 0.0415 watts or volt amperes. In the figure we have we have 0.0207 volt amperes, and for the source this is equal to 5 volts times the current of 0.0501 amperes, which gives us 0.2507 watts, and in the figure it's just 0.2500 watts. Okay. Notice that in the figures the current is multiplied by 100 as well as the power, so they are scaled to 100 in the reactive power in the capacitor and in the inductor, but in the apparent power and real power they're scaled to about 10. Okay, so what you see there are exaggerated graphs of the power and the current. Okay, and we have these values, and we can already explain the discrepancies between these values. These values that were initially computed were just based on the maximum amplitude of the voltage and the currents, but these values that were computed next and seen in the figure were values obtained when multiplying the two waveforms by each other. Okay, and the difference and the discrepancies arise because they are because the curves due to the reactances are out of phase. Okay, so if we go now to the power triangle, this is what it looks like. Okay, we have the real power for which we obtained from the power across the resistor, and the reactive power and the apparent power, and here the power factor is approximately equal to 1. You notice also that the reactive power is scaled by 100, so that means that the angle is very, very small. It's actually 4 degrees, and this results to a ratio of the real power and the apparent power that is approximately equal to 1, or In this case, if we round them off, then we get a power factor of about 1.